Hey, Shio, hello, and a warm welcome to the 18th speaker series, A Sense of Place, Indigenous Perspectives of Land, Water, and Sky. Today, we are very honored to host Dr. Nour Rawafi, project scientist of NASA's mission, the Parker Solar Probe. We also have Dr. Kelly Korek from NASA. She will be joining us, and we're very grateful. She will be fielding our questions at the end of Nour's presentation. This series is hosted by the Indigenous Education Institute. Today's session is supported and funded by NASA HEAT, the Heliophysics Educational Activation Team, led by Dr. Michael Kirk. My name is Nancy Maryboy. I'm Diné and Saligi, Navajo and Cherokee. My Cherokee name is Tsawayuga, and I'm from the Cherokee Bird Clan. I'm also of the clans of the Diné B. Bitwoni Deer Springs Clan and Tsinjakini, the Cliff Dweller Clan. I'm the founding president and executive director of the Indigenous Education Institute, which has been in existence for almost 30 years. We are located in the San Juan Islands of Washington State and on the Navajo Nation in Arizona. I would like to begin today with a heartfelt acknowledgement of the Indigenous peoples of our Mother Earth, to honor our many participants from around the world. Usually we acknowledge the land on which we are living or presenting, but in this day and age of virtual online realities, as well as the pandemic of COVID-19, we wish to honor all Indigenous peoples around the world. I also want to acknowledge that I currently reside on the ancestral lands of the saltwater salmon people of the Salish Sea, who have called this place home since time immemorial. I honor the inherent and acquired treaty rights of these Indigenous peoples. The presentations in this series have been chosen to reflect an awareness of the foundations of traditional Indigenous thinking and living. In our native ways, everything is interconnected. So rather than a specific focus on biology, astronomy, or other separate disciplines, we will be presenting dynamic worlds of interrelationships and processes of reciprocity. An additional focus for this speaker series is expanding awareness and understanding of cultural differences, and to support successful and diverse collaborative working relationships, whether it be at NASA, Johns Hopkins University Applied Physics Laboratory, the National Science Foundation, or in education, health, astronomy, national resource management, museums, science centers, and tribal communities. I want to thank you personally for attending this webinar. The interest you have shown is truly heartwarming. We have over 300 people registered from all across the United States. And we have participants from around the world, including many from Canada and others from Germany, Mexico, Puerto Rico, Saipan, Italy, and Indonesia. It is also interesting and heartwarming for me that we have more than 80 different tribes represented in our registrations for this presentation. That's 80 different tribes. We also have many classrooms that have registered for this event. I want to give a particular shout out to all the students and staff of Little Singer Community School, an all Navajo school on the Navajo Reservation, who are all very excited to hear from Dr. Rawafi, and Tom Thomas's class in particular. They're all listening in today. Before we continue, I would like to ask you to put any questions for the presenters into the question and answer box, not into the chat box. This will enable us to better serve you towards the end of this presentation. And again, we are honored to have Dr. Kelly Korek from NASA headquarters serve as our question moderator. I would now like to introduce Dr. Nour Rawafi. Dr. Rawafi is an astrophysicist and a principal professional staff member at the Johns Hopkins Applied Physics Laboratory. Dr. Rawafi is the project scientist of NASA's Parker Solar Probe mission, launched on August 12, 2018, which is the record holder of the closest human-made object to a star, i.e. the sun in this case, and the fastest spacecraft. The Parker Solar Probe will get as close as 3.8 million miles from the solar surface. Wow. As part of the Parker Solar Probe team, Dr. Rawafi received the NASA Silver Achievement Medal Award and the AAS Neil Armstrong Award. Dr. Rawafi is from Tunisia in North Africa. He received his PhD in astrophysics with distinction from the University of Paris, 11, I guess, or XI, in Orsay, France. He was a postdoctoral fellow at the Max Planck Institute for Solar System Research in Germany and a research associate at the National Solar Observatory in Tucson, Arizona. And one of my favorite things about Nour is that he has been a certified referee from the United States Soccer Federation, USSF, since 2006. And now it is my great honor to present Dr. Nour Rawafi.
Thank you so much, Nancy. And it's really great pleasure to be here with you to talk about the sun, about space, and a very exciting space mission that is Parker Solar Probe, and what we are learning from it, and what we can how we can see the future from now on. Parker Solar Probe is an amazing mission, but before going into that, let me give you a little bit background about myself. As Nancy mentioned earlier, I'm actually from Tunisia, which is this very small country around here. It's a tiny country, but for those of you who don't know, the name Africa is actually the original name of Tunisia. Back in the day, Carthage was one of the richest place on the globe, and the whole area was known as Africa, and then the continent inherited the whole name. So I was born there and raised there until I graduated from the university there, and after that I went to do my PhD elsewhere. So Tunisia is really, as I said, it's a small but a beautiful country. We have probably one of the best beaches in the world. We have also desert on the south. So it's pretty diverse, and it's a very, very welcoming country. And the name itself, Tunisia, it means that it's a welcoming place. So, and for history also, we basically have all civilizations going from the Phoenician to the Greeks to Romans, you name it. We have it's basically like a melting pot, and it's really a nice mixture. And moving a little bit now to modern ages, Tunisia is also the site where at least part of Star Wars was filmed. That is in the south of Tunisia, and here is one of the scenes. It's actually, you can find more about it on the web. And these sites are still there, and they are a touristic place that people can visit. And a little bit about my professional career. So I started in Tunisia until the age of 22 or 23. Then I left to France for my PhD, and then I spent a little time in Italy, just probably 6 months in Italy. But those 6 months basically changed a lot of things in my professional career. Then I moved to Max Planck in Germany, and I spent 4 years in Tucson, Arizona. And Tucson, Arizona is so close to my heart. I really loved that place. But when the opportunity came to work on Parker Solar Probe, I moved to the Applied Physics Lab at Johns Hopkins, and I'm at the APL for nearly 16 years now. And since I joined APL, I just got involved in Parkinson probe. That's which is very close to the hearts of many of us. So, so again, going back to my childhood, I was so fortunate to be born in the countryside, where on summer time, particularly at the night, you look up at the sky and you see scenes like this one. By the way, this image from Hubble, it's better than we see with our naked eyes, but still, when you have really a dark sky, you can see marvelous scenes out there. And I believe many of us were so fascinated by what we are seeing up there in the sky. And many of us, from a very, very young age, were asking questions that are fundamental questions. I mean, like, what are these things that are kind of glittering out there on the sky? Is there anybody out there? And by the way, is there anybody out there, which is probably a child question? It's one of the most fundamental questions that probably everybody wants to answer. It basically tells us, is there life elsewhere in the universe? And that's one of the top science questions for NASA and for other space agencies to answer. And by the way, I believe many of us there tried to even count stars, but that exercise did not really went that far, because when you look at the sky like this, there are so many stars. And these stars are nothing but suns. They are just a little bit far away. And talking about the sun, that's one of my biggest fascinations since a very young age. You cannot imagine how many experiments I did with the sun, trying, for example, to focus light from the sun, or to take a piece of plexiglass to basically, well, now I knew it, but back then when I was a child, I didn't know the physical concept, basically to disperse light in the different wavelengths. Basically, what I was trying to do is basically a prism. But later I got a very sophisticated prism. I did it much better than a piece of plexiglass. But still, until much later, for me, the sun was just that orange ball up there in the sky that we see rising every morning and setting late in the day, and wait for it to rise again on the next day. There is one thing that I learned from my child, from my son, who is 6 years old. Last year, when I was actually getting him ready for school, and it was winter time, and he was standing by the glass door, and he was not very cheerful. He's a very cheerful guy, but that morning in particular, he was not really, he didn't look like himself. So I asked him, Adam, what is going on? He told me, I'm not very happy. And I asked him why. He told me, well, the weather, it's been raining for 3 days. I asked him, what would make you happy? And without thinking even for a second, he told me, sunlight. For me, that triggered something. There is actually a connection between us and the sun. Even if we are not conscious of it, we are still connected with it, like our connection to Earth, like our connection to other places in space. So this connection is born with us, and it will stay with us forever. And that's probably where our fascinations with space, with the sun, with the moon, with Earth, and other bodies out there comes from. And after all, if you think of it, we are all made of stardust. Basically, we are all star babies. Whatever you look around you is actually basically debris from stellar explosions that happened in the past. But the sun is more than we see with the naked eye. The sun, when you see it from space and with sophisticated telescopes, you will see scenes like this one. That orange ball that we see with the naked eye every day is actually an extremely active body out there. It is magnetized, and the magnetic activity, like you see here, produces explosions basically on daily basis. And these explosions are so massive and they are so energetic that if I tell you the numbers, you cannot even imagine, you cannot even make sense of them, because the number is so big. Just let me give you one example. You take 5 events of like the one I just was playing in the movie. These 5 events produce enough energy to power to fulfill our current energy needs for some 200 to 300 years. No, 200, yeah, 200 to 300,000 years. And 200 or 300,000 years, that's basically the full span of modern human existence, which is kind of fascinating. But the sun does that in matter of minutes to hours. That's how much the sun is powerful compared to us. There is another aspect about the sun that many probably take for granted. Obviously, the sun is pretty far away from us, and we see it because of the distance. We see it very small. But the sun by itself contains more than 99.8% of the total mass of the whole solar system, including all the 8 planets, dwarf planets, asteroids, comets, you name it. Basically, the sun by itself is the solar system and is the driver of the whole solar system. And you go a little bit further. Those explosions that the sun produces will propagate outward, and some of us will come to us at Earth, and they affect us. If I take just one example, which is the storm that happened in May of this year, it produces scenes like this one. I think these are so fascinating. Yeah, I mean, you see aurora to very low latitudes, which is kind of exceptional. It's so marvelous. And I believe there are millions and millions of people who got attracted to scenes like this one, which is, you can keep looking at this for tens of years and you will not have enough of them. That's what the sun produces for us. And that's also another reminder of our connection to the sun. There is another aspect also that attracts us to the sun. And this year in particular is so special for us. I talked about the storm that happened in May, but just a month before that storm, we got a solar eclipse that crossed the US from the southwest to the northeast, which was also so fascinating. It attracted millions of people to look at the sun. By the way, this animation is for the 2017 eclipse that also crossed the continental US. What eclipses teach us about the sun is basically shows us another layer of the sun that we usually don't see with the naked eye. That is the solar corona. That orange ball that we see with the naked eye is masked here by when the moon comes between us and the sun. And after that, you see all the splendor of the solar corona. Look at these shapes. Look how complex they are. They are complex, but they are so marvelous and beautiful. But that complexity actually hides behind it very mysterious phenomena. And some of these phenomena are so perplexing that they were discovered decades ago. But to this day, we are still trying to understand them. Some of these phenomena are, for example, what we call the coronal heating. The corona that we see during the total solar eclipse is millions of degrees hot. But the solar surface itself that we see with our naked eye is only 6,000 degrees. So the corona is over 300 times hotter than the surface, which is counterintuitive. Because if you take from everyday experience, if you move away from a heat source, it cools down. But obviously that does not work for the solar corona. This phenomenon was discovered in the late 30s. And to this day, we don't have a full understanding of it. That boiling gas in the solar corona that is multi-million degree hot cannot stay static. It will produce a flow of charged particles that are electrons, protons, and heavy ions that will flow away from the sun to fill the whole heliosphere. That's what we call the solar wind. And the solar wind is also the other side of the mystery. I mentioned the coronal heating. The other side of the mystery is the solar wind. Because when you look at the plasma lower down near the sun, it doesn't move at very high speeds. Speeds that are ranging from 5 to 10, 20 kilometers per second. And 20 kilometers per second is extremely fast for us here on Earth. But up in space, it's basically nothing. The mystery about this flow of particles that over a very short distance, these particles start flying at hundreds of kilometers per second. And there again, we don't really understand where they get the energy to get accelerated so fast. The third phenomenon is related to that explosive activity that I talked about earlier. Whenever you have flares or coronal mass ejections erupting from the sun, they erupt a certain population of particles to almost the speed of light. We call them the solar energetic particles. And these what form a hazard to space equipment like satellites in space, like humans in space also can be exposed to this. And when they are severe enough, they can actually affect us here on the ground. One concrete example of the impact of solar activity on the Earth environment is the loss by SpaceX of 40 satellites last year. I have a movie, I will find it later to share it with you, but it's really fascinating to see a moderate solar event that caused all these 40 spacecraft to decay and burn in the Earth atmosphere. Imagine if we have a big, huge event like the one that was in 1859, the Carrington event. That would be so fascinating, but it can be also, the consequences can be also pretty severe. And that's actually why we are so interested in the sun, because we depend on the sun. Our lives depends on the sun. Actually, we exist because of the sun, thanks to the sun. But on the other hand, if we want to keep all the technological progress and prosperity we achieve, we have to be watching for space, because our lives, in a way, will be driven from space. They are actually currently partly driven from space now, but in the future, we are going to rely more and more and more on space. And that's where a mission like, sorry. And that's actually where a mission like Parker Solar Probe comes in. The phenomena I described earlier, they were discovered decades ago. But observing the sun from afar helped a little bit, but didn't really help solve these mysteries. We needed the probe to fly as close as possible to the sun and give us local measurements there to tell us what is going on. And that's why we needed Parker Solar Probe. And just for history, the idea of flying a spacecraft close to the sun is not new at all. It dates back to 1958. 1958 is when Eugene Parker, after whom we named the mission, made the prediction that should be a flow of particles flying away from the sun. He called it the solar wind. On that same year, there was a commission that worked came up with a report on what missions we should implement to understand big phenomena out in space. One of these missions is the solar probe. And NASA has tried many times to implement the mission, but none of them came to fruition until 2008, when we find the right material to build the heat shield that will protect the spacecraft when it is close to the sun. Then NASA decided to go ahead and build the mission. In a way, we were actually trying to mature the technology to the point that we can fly a human-made object close to a star and fly it safely. And that's actually what we did with Parker Solar Probe. And since 2008 to 2018, it took us 10 decades to build this spacecraft because it's so sophisticated. And as I was joking with one of our engineers here at EPL and saying, yeah, we spent 10 years building a spacecraft that is 3 meters high. And she told me, you know what, we spent 10 years breaking stuff. And she was absolutely right, because to build a spacecraft as sophisticated as Parker Solar Probe, you have to push materials and systems to their breaking point and see whether they are adequate for the environment near the sun or not. Yeah, this is the heat shield I was talking about earlier. This one, actually, it has a story behind it. As I mentioned earlier, NASA decided to go ahead with the mission in 2008, but it commissioned the Applied Physics Lab in 2001 to start looking into material to build the heat shield. It took us a little bit over 6 years to come up with an answer that we have the right material, we know how to build it, and then NASA decided to go ahead with the mission. It took us from 2008 to 2018, but 2018 marked really history. By the way, do you hear the sound or not?
There's no sound.
Okay, just let me stop sharing and I'll share again.
Of the mighty Delta
What about
4
now?
Heavy rocket with NASA's Parker
Yeah, we've
Solar
got
Probe,
sound now.
a daring mission to shed light on the mysteries of our closest star, the Sun.
RS-68 look good in the full thrust mode. "25 seconds into flight. Chamber pressures continue to look good on all 3 boosters. Now 35 seconds in. Chamber pressure on the core booster is throttling down to the partial thrust mode. Response looks good. Now 50 seconds into flight. Strap-on boosters look good in the full thrust mode. Core booster looks good in the partial thrust mode. Now 1 minute into flight.
So, and this is the team basically watching from the operations center here at EPL. They are watching the launch live. And by the way, when I said it's just the team, it's really a very small part of the team, because the team is so big. If you take from when we started Parker Solar Probe until we launched it took more than 3,000 people getting involved in Parker Solar Probe. It was not 3,000 people continuously working on Parker Solar Probe, because people comes in and go. But it took also more than, I believe, 10 million hours. Yeah, it's actually in the millions. I'm not sure if it is a million hour or 10 million hours of work to build the mission, which is quite fascinating. So let me tell you a little bit of story about launching Parker Solar Probe. So this is a mission that we have been waiting for 60 years. And the careers of many of us basically hinges on the success of a mission like Parker Solar Probe. And many of us were really nervous when the rocket was going up, and we were hoping everything will stay all together and everything would go fine. And effectively, things went fine. But I was at the Cape Center, the Kennedy Center, and behind me on the wall there was a watch. Basically, it starts counting when the rocket start going up. It starts counting. What seemed to be like 30 seconds, I turned around. It was close to 6 minutes, and that, in a way, it's basically everyone is focused on what is going on and hoping that everything goes fine. That we don't really see the time flies passing by. So let me go a little bit now back to the sun and what is the science we want to do with it. Some of the big mysteries that we want really to solve for so long is, how comes the sun produce an extremely high gas around it. And also how comes that gas managed to escape the sun's gravity to form what we call the solar wind. And in a way, what we're looking for is how that plasma, where the plasma gets energy to beat the solar gravity. The solar gravity is so huge. And for a particle to escape the gravity, it has to start with a velocity of 600 kilometers per second. Or it has to be accelerated as it is flying away from the sun. And it's now we started really getting some insight on what is going on, thanks to Parker Solar Probe. So when Parker Solar Probe flew close to the sun, it gave us a view that we did not really see before. Basically, what it showed us, that we see ripples in the magnetic field. They are like folds in the magnetic field. They are all over the place. We call them reversals, magnetic field reversals or switchbacks. And the fascinating thing, by the way, these have been seen before, but they were rare, far away from the sun. And they have been seen a few times before, but people didn't really pay much attention to them. But when Parker Solar Probe got closer to the sun, it was so fascinating to see them all over the place. And what is really nice about them, they are highly energetic. They come with a lot of energy with them. And for us, they probably represent the smoking gun that will help us understand what heats and accelerates the plasma over there. But let me tell you a little story about this. So when we first saw them, some of us thought probably there is something wrong with this. And honestly, it probably didn't feel that good because, yeah, we have been waiting for this mission for 6 years. And if the first thing you get is a problem of some of the instruments, it doesn't really bode well. In particular, that we were planning to share the data with the public soon after we got the data. We got that data, but it took us not really long at all to find out that everything checks out, and actually what we are seeing is something new that nobody has predicted before. So trying to understand how these switchbacks form and where they come from, and how they evolve in the solar wind is actually helping us to understand how the solar wind continues to be heated and accelerated as it flies away from the sun. It is also pointing us to the origins of the heat and the acceleration of the wind near the sun itself. I think we are not there yet as far as how the solar wind escapes the solar gravity, but we are so close to it. So in a way, Parker Solar Probe is helping us answer this big phenomena that was designed for, which is so fascinating. But on top of that, it is helping us discover new phenomena that we didn't even know about. And when you look at the data that we are getting from Probe, it's so loaded with new things that we didn't know about, that actually we don't really have the time to look into all of it. So in a way, the data we are getting now, it's going to serve many generations to come, which is kind of fascinating. That's why we built missions so audacious like Parker Solar Probe. But Parker Solar Probe is not only built to observe the gentle flow of the solar wind. It is also built to withstand big explosions of the sun, like coronal mass ejections, like the one we are seeing here, which erupted on September 5th, 2022. When this event erupted, Parker Solar Probe was on the backside of the sun. So for days, we don't really know how it was doing. Something we knew that actually this coronal mass ejection actually hit Parker Solar Probe. But we had to wait for several days until it emerged on the other side to find out how everything went. But obviously, Parker Solar Probe dealt really well with this event, despite it was flying at more than 2,500 kilometers per second. And Probe at the time was very close to the sun, very, very close. From this event, we learned so much, but I'm going to let you listen to this audio of the event itself. So what we're seeing here is a probe is as I said, is flying close to the sun, and it was measuring and observing the normal solar wind, and that's what we hear at the beginning. But all of a sudden, you have this big shock wave that is hitting the spacecraft, and actually that's when the shock hits the spacecraft, you hear it really well in the audio. But also you see this big thing just in front of the spacecraft. That is actually the coronal mass ejection itself. And the fascinating thing about it is that for a long time, from observation near 1AU, near Earth and elsewhere, we thought really we have a good understanding of the structure of this coronal mass ejection. But Parker Solar Probe is giving us a new view. The complexity, the internal complexity, the complexity of the internal structure of coronal mass ejections is totally out of this world. And it's really sometimes, I would say, it's a little bit scary because what we thought we knew actually turns out probably not correct at all. The other thing that also we learned from Parker Solar Probe as it flew through the event itself, it showed us that these events basically clean everything in their way. They basically leave a near perfect vacuum behind them. We kind of understand how the particles gets carried away by the magnetic fields of the event, but the heavy dust particles, those are pretty heavy, but still they were actually also cleaned away by the event, which is fascinating. And after that, you are flying through that near perfect vacuum for hours until new material comes from the base of the solar corona to repopulate that region of space. And that, in a way, it tells us how these events, when they hit us here on Earth, how much activity we get, geoactivity we get up in our atmosphere. It's really no brainer at all because they are so energetic and they can be very, very impactful on the environment they fly through. Parker Solar Probe is also not only about the sun. There are other aspects of the mission that we use it for. This is just one example of them. So we use Venus to get closer to the sun. And for the whole mission, actually, we used Venus 6 times, and November 6th of this year, we'll use it for the last time, 7th time. And every time we fly by Venus, we get that from that gravity assist, what happens is we slow the spacecraft a tiny bit. And when it gets slower, it will actually dive closer to the sun. And that's how we get closer and closer over the 7 years to the sun. And whenever we fly by the sun, in particular when we are flying behind the planet on the night side, we try to observe that atmosphere. And one of the ideas that we had is trying to image clouds in the atmosphere of the planet. This is the black and white is actually our image from Parker Solar Probe. And when we got it, we thought, yeah, these are probably the clouds. But we actually soon after that, we found that the Japanese mission Akatsuki had almost identical image, but it just, that image was taken a few years before Parker Solar Probe launched. So obviously, these are not the clouds. For us, the story was kind of exciting, but basically it stopped there. But our friends, the Venus specialists, when they saw this data, actually they saw something different in it. They got the data, they analyzed it, and guess what? They discovered a new wavelength band that allows us to observe the surface of Venus. In a way, Parker Solar Probe opened a new window to study Venus. And the future missions like Veritas and others will actually will take benefit from this discovery to study the surface of Venus. The team did not even stop there. They went and analyzed the brightness that we see, the brightness we see here on the surface of Venus. And what they are discovering, that actually the rock formations have different compositions, which is actually the science objective of these future missions. As one of our, the team told me, in a way, Parker Solar Probe is scooping this future mission. But what is fascinating, this observation by Parker Solar Probe is so fundamental that recently I was at a conference, COSPAR, and I was at one of the sessions talking about Venus. And actually people refer to it as the Parker Solar Probe observation. It's kind of a reference now, which is fascinating. By the way, the dark area here is the Aphrodite Terra. It's a high plateau on the surface of Venus, and it's a little bit cooler than the rest of the surface. Obviously, Parker Solar Probe is not only about the sun. It's not only about space. It's also about us humans here on the ground. When you have a mission like Parker Solar Probe or James Webb, or in a way, it helps us who are we, what is our place in space, and how we came about, and then probably where we are going. And the excitement you see from very young age up to to adults is fascinating. This, for example, this picture here is actually, we were distributing sunglasses for the eclipse, and people were wearing them on the airplanes, which is kind of fascinating to us. We bring the Parker Solar Probe to the whole community, and we are so glad that the indigenous communities are so probably at the center of our interest, talking about the mission and about our science in general. And this is not only the Parker Solar Probe, but all the other missions that NASA is building. We actually want to bring them out there to the public. Let me conclude by this. So we built Parker Solar Probe, and we launched it in 2018. And the goal was to get to the closest approach ever to the sun. To us, that is so historical, because getting so close to a star is not really an easy achievement at all. It's one of the hardest things you can imagine. But on Christmas Eve of this year, that will be Parker Solar Probe will be making history. It will reach 3.8 million miles from the surface of the sun. 3.8 million miles is a big number. But if the Sun-Earth distance was one meter, Parker Solar Probe will only be 4 centimeters away from the sun. That's why we call Parker Solar Probe a mission to touch the sun. And that's why Parker Solar Probe is so close to our hearts. And it's not only that, it is really helping us to understand this star that our lives depends on. Let me conclude by this. I started with a dream of a child, and that dream, when I was younger, trying to understand what the surroundings. Actually, it actually grew and grew and grew, but I could never imagine that I'd probably get to where I am now, and will be a member of a big team that's doing a marvelous thing, building spacecrafts like Parker Solar Probe, like James Webb, and trying to understand our origins, our presence, and also our destiny. And I will just end with this picture from James Webb, which is so fundamental. We started with the dream of a young child, but also will end it with a dream of scientist, which is still acting like a child, trying to understand what is out there in space. Thank you very much. And if you have any questions, I'll be happy to answer them.
Thank you. Chris, can you put back my screen? Thank you. Nour, thank you. That was a wonderful presentation. I'm just fascinated by it. And I'm so glad we recorded it and we can watch it again and again.
Thank you.
I love the way you can bring such complex thoughts and concepts down into even everyday English, so we can understand them, and our students can understand them. And it was just so nice to have you here.
Thank you. Thank you.
So this has been a very memorable session.
Thank you.
Now we do have some questions for our speaker, and I'm honored to introduce our friend and colleague, Dr. Kelly Korek from NASA headquarters, and she will field the questions and answers for this part of our webinar. It's interesting, you may be interested to know that Dr. Korek was the director for NASA's coverage of the total solar eclipse in April 2024, which was a huge effort. We were in Dallas, Texas, David Begay and I, and it was a grand experience. And she's also a key part of the Parker Solar Probe. So who could
Absolutely.
to ask the questions than Kelly? So Kelly, would you please introduce yourself?
Definitely. Thank you so much, Nancy, for having me here. And thank you, Nour, for that great presentation. My name is Dr. Kelly Korek, and I am originally from Michigan, and I have 3 degrees from the University of Michigan, and then I've spent time with working with the Smithsonian up in Boston, and that's where I got the pleasure of working on Parker Solar Probe, and then moved to NASA headquarters a few years ago, and had the joy of, again, experiencing the eclipse, as well as really sharing NASA science with everyone. So that's a little bit about me. And in addition, I also am a yoga teacher. I have a lot of different interests, and I have an amazing cat who you visited in the call that Nancy and I had before this. So there's many different aspects to a person. And so some of the questions that came up for Nour, I actually had a few too. So talking about people and stories, and I think of Parker in some ways as a superhero, right? This is such an amazing, amazing spacecraft that is going faster than any other thing we've built. It's going farther than anything we've built. So every superhero has an origin story. So what about Gene Parker, the person that this spacecraft is named after? Do you have any stories or any kind of inspiration as to the name that is on our probe?
Yeah, thank you, Kelly. Yeah, Gene Parker is really exceptional. First of all, let me start by saying he's really a very humble person when you meet him. He's a giant in science and in knowledge and everything, but as a human, he's very, very humble. And the story about Gene Parker is so fascinating. I always call him the heliophysics monster in the good sense, because he's so good in everything he does. But when he was young, actually he wrote this paper after a discussion with a German physicist called Biermann. And when he wrote it and submitted it to many journals, all of them basically rejected it. They did not want to accept it because it's new predictions. Nobody wants to publish this paper. And I believe the anecdote goes that at least one reviewer told him that he probably should go to the library and learn more about the sun and its environment. But they took one Nobel laureate, which is Chandrasekhar. He was actually the editor of the Astrophysical Journal. And the story goes that he told Gene Parker, they were actually in the same institution, by the way. He told him, yeah, your paper might be ridiculous, but I'm going to publish it anyway. That paper basically changed the history and the direction of heliophysics research. It was so fundamental. And to me and to many out there, if somebody tells you what you are doing is ridiculous, actually it might be original, except that people don't really understand what is it all about. Never take what people tell you about what you are doing or about yourself in a negative way. Sometimes when you come up with new ideas and new concepts, people will not accept them necessarily. If I just draw a parallel, about this. And this is really a real story here at the Applied Physics Lab. I think we are all probably familiar with the mission DART that we basically launched and smashed an asteroid with it. When this scientist here at TPL came up with the idea several years ago, some of the engineers here at EPL told him, this is probably the most ridiculous idea ever proposed. Guess what? That was one of the most fundamental, achievement in recent history. Again, I cannot say it enough. Gene Parker for us is a model. He's so sure of the science he does. He's so humble. He's so approachable. And he's most of all, he's very open-minded. And that is really fundamental for the progress to go forward.
Definitely, yes, that's so important. And I think in talking about having different viewpoints and maybe that's a great way, or you're onto a discovery in science. We had a question written in about how can I, as an educator, assist academics and educators implement a paradigm shift in the portrayal of Indigenous learned knowledge and science-centered constructs that were instrumental in establishment of a sophisticated agrarian Indigenous civilization. So I think, again, going back to the how do we take knowledge that's already there that maybe some folks just don't understand and bring it into the forefront.
Let me. This is really very, very important question, and thank you for asking that, Kelly. You can learn about ancient civilizations and indigenous communities here in the US is part of that. They knew so much, except part of that knowledge is lost. And the loss is basically the lack of documentation is part of it. The loss can result from miscommunication. That the science is not communicated, the knowledge is not communicated. So in a way, the responsibility is not only on the indigenous communities, it's also on us. We really have to go toward the indigenous community and try to understand what do they know? What is the philosophy behind it? That's extremely important. Documenting also this science that the different communities come about is extremely important. NASA and other agencies now are doing some effort, but we still have a lot of distance to go to get there. And I think we have both of us have to come from both directions and basically meet in the middle. That way we can understand each other better. Like today, it's so fascinating. Well, not today. I gave a talk a while ago. And I learned more than I gave during those discussions, which is fascinating to me. Just I can give you one example, because I'm also kind of come from a different part of the world where some knowledge was invented, but in a way, part of it is lost. Until recently, somebody here in the West reminded me of something. He told me, if you look up at the sky, 2/3 of the known stars have a name from one civilization, which is so fascinating. And many people don't know it. Meaning to me that these ancient civilizations, they knew so much, they invented so much. And if we don't preserve that knowledge, obviously it will be lost to be rediscovered again by other people later.
Excellent. Yeah, there have been several questions both in the chat and before about the Tunisian traditional knowledge, and was there anything that shaped your perspectives on the sun based on that experience?
Yes. Well, since a very young age, I was so interested in the history of science and how people came to discover big things. And one of the aspects that really attracted me so much is about solar eclipses. And I looked so much into it. And what I discovered, what I learned early on, is that even if you go to the ancient civilization like Babylonian or even the Chinese before them, they exactly knew when an eclipse is going to happen and where it's going to happen. So they knew the math. They knew the orbital motions of the planet, of the Earth, the Sun, and the Moon. They knew all that because they exactly go. They actually organize expeditions to observe these eclipses. To me, again, it goes back to the question you asked earlier. Yeah, these people probably invented so much, except we are not very fortunate to capture all the knowledge. Going back to my background, yeah, there is a lot that have been invented, not in Tunisia, because Tunisia was part of a bigger civilization, which also brought, in a way, what happened. They brought all the bright minds of all over the world to build that civilization. That is extremely important. If we are not open-minded, if we are not welcoming, you cannot build a civilization. It's as simple as that. And if you look at us here in the US, we are actually attracting the most brilliant people from all over the place. That's actually why the US is so advanced compared to many other places.
Interesting.
Definitely. That's very, very interesting. And I think that actually leads a little bit into one of the other questions we had submitted previously. It's what are better ways of bringing Indigenous knowledge, perspectives, and decolonizing, re-indigenating practices to institutions of higher education and the government grants that typically fund these aerospace and high profile expenditures on research?
Yes, there are many initiatives now that basically try to be inclusive of minorities and all that, and all of us have to benefit from it. It's not only, in particular, about knowledge and about science and all that. It's not only the indigenous communities; even other people can actually apply to these opportunities to work together with the indigenous communities as well. It's extremely important. For us, for example, within the Parker Solar Probe project, we have funds that basically goes toward specific communities to bring us toward us. For example, fund certain people, if possible, to work on Parker Solar Probe, but also try to educate and learn in the same time. We have a full program that we developed for this purpose. And I think going forward, the same thing. We have to benefit from the opportunities that are out there, but also we have to create other opportunities. Whenever a big mission comes by, we have to be inclusive from the get-go.
Definitely, definitely. And speaking about the probe, I'm going to kind of swing back to some of the questions I see in the chat about that. So first of all, will the probe eventually get too close to the sun and stop functioning?
Well, at a certain point, it will stop functioning, but the Parker Solar Probe will not get closer to the sun. It will not get closer to the sun because it was not designed for, but even if you leave it for itself, the orbital dynamics will not get it closer to the sun. It will stay in that orbit and probably it will move a little bit further out. But the gravity of the sun will not attract it toward the sun. Yes, by the way, I have to say that after 6 years up in space and getting close to the sun every 3 months, Parker Solar Probe is really very, very healthy spacecraft. It's working so well. It's basically like we launched it now, which is fascinating. And I'm hoping it will continue like this for many, many years to come. And that's also thanks to all the effort that everybody put into this mission. So what we are talking about now is how to extend the mission as much as we can. And as the Friday of last week, we actually have a meeting with NASA headquarters talking about the future of the mission, what we are going to do about it. And NASA is extremely excited about the mission, like Kelly can testify to that. Yeah, the mission is pretty healthy. It will continue to work, but obviously at a certain point, hopefully far in the future, the mission has to end. And when it ends, the only thing that will happen, we will not be able to keep the attitude of the spacecraft. And when I talk about the attitude, is basically this. So this is the heat shield I was talking about earlier. For now, when we are closest to the sun, spacecraft, this side has to be always facing the sun. Basically, the body of the spacecraft has to reside in the shade of the heat shield all the time. But later, when we stop the mission, basically we will not keep the attitude of the spacecraft. It will start tumbling, and parts of the sensitive parts of the spacecraft will be exposed to direct sunlight. They will get damaged, but the overall body of the spacecraft will stay in orbit for a very, very long time.
Yeah, definitely. So there was another question of, they say, I love that some unexpected discoveries around Venus were made. Did that change plans for subsequent passes by Venus?
Yes, I changed the plan. The next Venus flyby, which by the way, it will be the last one in the prime mission. It's the 7th. It's in November 6th. So from what we learned from the previous Venus flybys, for this one, we actually started working on it a year and a half before, planning for it. And the reason for this is pretty simple. The previous Venus flybys, we were something over 2,000 kilometers away from the surface of the planet. For this one, we will be only 380 kilometers. We will be so close to the planet. And from the imaging perspective, the spacecraft is moving quite fast. If you expose your images as we usually do, you will get a lot of smearing. So what you have to do, you have to build a custom observing program just for this Venus flyby. And we tested it twice already. It's working perfectly. And we're expecting so much from it. We basically want to have the shortest exposure times for these images to beat the smearing and trying to resolve as much as we can from what we see on the surface of Venus. So the expectations are pretty high. And also the nice thing about this Venus flyby is that we would be flying so deep into the atmosphere of the planet. And honestly, I don't know what we're going to see. So we have just to wait for the data to come down and see what is in the data.
That is a good part of this is to see what's next and to find those unexpected things. Yeah. So another 2 questions came in, and so I may have missed this, but what examples of Indigenous knowledge from your people are present in your project design and are yet practiced and evidenced that you're able to share or expound on?
Well, in terms of technology, I'm not sure. There is definitely the math. The algebra is was actually invented into the Arab-Muslim civilization. So algebra is everywhere. So that's a fundamental thing. There is a lot of math as well. But let me give you a little story. Years ago, we were in a meeting talking about Parker Solar Pro, and somebody mentioned the word nadir. And I was pretty sure that this word is actually not an English word. And I went to look it up. And for me, yeah, it sounded like Arabic. But actually, the Arabic word, it's an Arabic word. It means looking up. It is direction up. Nadir. For us, it's nadir, but it's actually borrowed, and there are many other terms that are also borrowed but they are used in astronomy in general. But let me tell you one thing. If you talk about technology, cameras, actually the word camera itself is an Arabic word. And cameras, the first camera invented was actually invented in the Arab-Muslim during the Arab-Muslim civilization. And a camera is camera in Arabic, and that's I forgot the name of the guy who invented the dark chamber, but that's actually was first invention. But that's actually where modern cameras came from. At least the principle came from there.
Great.
So
Right, there
coming back to
Go ahead.
that ancient knowledge, although it might be very simple back then, but still it gets developed to be so sophisticated now.
Yeah, so there was another comment is I've heard the Earth at one time was dark for a period of time due to what I don't remember. The darkness had a large negative effect on life on Earth. Why couldn't the sun's rays reach the Earth in that situation?
I'm not sure. I'm not sure what are you referring to.
Yeah, what comes to my mind is actually the Maunder minimum, maybe, or when there's a volcanic
Yeah,
activity
yeah,
and there's some clouds that
yeah,
form that tend to
yeah.
cause sunlight to not reach the ground.
Yeah, I think I thought about that too. I think, and I think you're right. But I think the other periods as well. It's during the ice ages, the big ice ages. The sunlight didn't really reach much Earth at all, and that's why it got so cool and everything basically frozen. Yeah, it's basically atmospheric changes up there. The atmosphere becomes so thick, so most of the sunlight is absorbed up there, and not much of it comes to the ground.
Okay. All right. So how are the discoveries of Parker Solar Probe affecting the study of other stars?
Oh, this is really a fascinating question. So the sun is the closest star to us, and we know it better than any star in the whole universe. We know it in so much detail, and those detail that we cannot get about any other star out there in the world, in the universe, because they are so far. So in a way, whatever model we built about our other stars, the sun has always something into it. We always go back to the sun as a reference. For example, the heating and the acceleration of the solar wind. Other stars have also their stellar winds as well. So that knowledge, you made observations out there about star, and you go back and compare them to our solar wind. So the discoveries from Parker Solar Probe will help us also understand other stellar environments. There is one discovery by Parker Solar Probe, and still it's a little bit, we have to settle it down. It has to do with the how the sun loses momentum. When the sun was very young, it was rotating very fast, but as it ages, it slows down. And Parker Solar Probe is giving us some hints about it. And to me, that discovery is more of a stellar discovery than a solar discovery, because it's really about losing angular momentum out there in every star, and it applies to all stars and basically the whole universe.
Definitely, definitely. And two last questions that I see so far. So could the probe provide data that would help solve the problems of sustained nuclear fusion on Earth?
Well, Parker Solar Probe is not designed for that. It will not provide. But as a matter of fact, we are actually thinking of a mission like Parker Solar Probe that might help in that direction. I cannot say much about it because it's still an idea, and but yeah, it's maybe, yeah, it can give us some hints if this mission comes to fruition. Yes, it can. But Parker Solar Probe was not designed for that.
Great. So there's a very great question here. How was the sound recorded in the vacuum of space?
Oh, fantastic! That's really good question. By the way, that sound is not basically what we took the fluctuations in the magnetic field and we made a soundtrack out of them. So you take any fluctuations out there in any quantity, you take it density or temperature, and you can actually turn it into sound. And that's what we did with Parker. Parker was measuring the magnetic field, and the magnetic field was fluctuating all the time. And we took just the fluctuating part of it and made a sound out of it. Basically, what we were looking at is variations in the magnetic field. And that variation, you can either look at it, you can quantify it, or you can hear it as well.
Great, great. Yes, I was actually wondering that too, as to how that happened. Now, reading through, I don't see any more Q&A. I saw one more comment that I kind of wanted to kind of close out. There are design, culturally sensitive and relative Indigenous research methods, and this is a way to allow the voices, kind of more voices in. So I might, we should perhaps encourage ourselves to embrace that and figure out how in missions going forward and in Solar Probe, in terms of, I feel we're really stewards of this great mission, because there's data that will be around for as long as folks would like to learn about this star, our star, as well as other stars, and apply it to that. So I really, wondering, like, do you see a way that we could perhaps try different research methodologies with Parker Solar Probe, and really bring in the Indigenous communities?
Yeah, absolutely, there is, and I think we should do them with Parker Solar Probe, but I think it's more for the future. It will be more significant in the future, because for the future, whenever you have a big mission, from the get-go, you have to bring in the Indigenous communities. It's not, don't wait until then. And when I'm talking about the Indigenous communities, my dream, if there is a big mission like Parker Solar Probe, is to get some students that get involved in the mission from the get-go, building hardware, doing science with it. Basically, they grow with the mission as we go. And that's, to me, that will benefit them. It will benefit the whole team. It will benefit everybody, because they will be learning from both sides. And that actually goes to the very first question you asked when you say, how can we share the Indigenous knowledge? Actually, sharing knowledge on both sides. And the best way to do it is basically build the team has to be so inclusive from the get-go. And that's the best way to do it.
Definitely. And here's another great question came in. How has your perception of the sun when viewed as a child changed with the vast amount of information that the probe has provided? Do you still feel awe when you look at the sun?
Well, let me tell you a little story about this. My son, he's really interested in space. He's still very young. Okay, and about a year and a half ago, I asked him, Adam, what is that bright thing up there in the sky? And he told me, Dad, how many times I have to tell you that's the sun? And then we went to talk about it, and he asked me afterwards, do you really look at that sun every day? I told him, no, yes. It happened that same evening, I was looking at a movie from the Solar Dynamic Observatory of the Sun. And he came close to me, and he put his head on my shoulder. And he was so absorbed into that movie. He didn't say a word. I played the movie again. He watched it again. And after that, I told him, Adam, what do you think? He told me, it's amazing. And he went to play with his toys, and a little bit later he came to me. He told me, Daddy, don't you want to look at the sun again? And I played another movie for him. So for me, I still have that little child in me. Whenever I look at the sun or look at other things out there, there is always something that will impress you, that will have an impact on you, that will get your attention, get your curiosity. I think we are born as children, and I think we will grow as children forever. So, and that's actually the best part of it. Yeah.
Definitely, I agree. I know that my earliest memory is of the sun, and it still inspires me to this day.
Absolutely.
I look at it every day. And when I need inspiration, I go outside and make sure
Exactly.
to feel the sun on my face, or feel the warmth. Because that's really the way to know that that's why we're doing this, right? It's not just, it's amazing, beautiful imagery. It's really to understand and to be a part of that. So with that, we don't have any other questions or comments at this point in time, and I will then turn it over to Nancy.
Thank you,
Okay.
Kelly.
Well, I can't thank you enough. This has been so interesting. I want to add one little story to your discussion. What we're doing with our NASA HEAT team is we've been working on this for about 1.5 to 2 years, and it's led by Dr. David B. Gay, my research partner, our research partner. And it's developing a Navajo lexicon. And so what we're doing under with the great support of Michael Kirk is we have spent tons of time together in person, even to describe the heliophysics concepts. It's more than just words, it's concepts. And so to develop those, and then in tandem come up with the old Navajo concepts that match up with it. And knowing that the Navajo language is a language of everything is interconnected. So it's a different way of looking at the universe because everything is interconnected. Going through those eyes and that mind to match it to the heliophysics concepts, which people like Michael helped us understand and have the right wording for. And so we're going to have this lexicon developed. It's just got one more thing to go, and then we're going to develop a poster to go out through NASA and go in a lot of the schools all over the country. And we hope it will inspire other tribes and their languages to dig deep in with this different way of looking at the world, and develop their own lexicons. So this is happening, and I really thank NASA for supporting this effort, and we're excited about it. And then we decided a couple of days ago we'd also include a recording, so elders who wouldn't read the language necessarily would be able to understand it and hear it. So we're adding that component to it now. And then we have such good relationships as Indigenous Education Institute with NASA and Johns Hopkins Applied Physics Lab. And the things we're doing with the missions particularly is getting funding from groups like the Solar Probe, and we're buying equipment for the schools, middle schools, STEM students. And so they're getting things like 3D printers and Lego prime sets and all of these different drones. And then they're using them in ways that they design, that's student-led, what they would like to create in a makerspace platform. And so we're very grateful for this funding. And what we do is just make sure it gets to the schools that need it. We have 8 schools right now, I think. And then Chris is running our test beds. And so every day we as IEI are actually working with the Parker Solar Probe and putting all this into the hands of this classroom teachers. So that's just an example of how we can bring the two ways of knowing together in a small way, and hopefully it will hopefully it will grow, and more of the missions will incorporate it, more of the NASA projects will incorporate it, and more of the Indigenous people will. I did see one chat that said, thank you so much. Thank you so much for bringing this into our, this idea of scientists working with native knowledge. And I thought that was a really nice comment to see in the chat, because that's how this is a give and take. It's not just all taking, it's not just all giving, it's sharing. So I think this has been a really interesting session, and I cannot thank you enough for both being on it.
Thank you.
The recordings will contain the entire webinar, and there's no cost to download them. Chris will put it on the chat, I believe. But you go to our website, which is www.indigenouseducation.org/multimedia, and you'll be able to download them for free. And a lot of people are using them for curriculums at a college level and classroom K through 12 level. So this one day has it's like a pebble being thrown into the water. It's going to go out and out and out. In closing, I want to extend a very special thank you to our technical support, Chris Tarrant of Tarrant Solutions in Friday Harbor, San Juan Island, Washington. Each time we host one of these speakers, there is so much work that goes on behind the scenes. The coyote factor, which is a Navajo disruptor and bringer of chaos, is always lurking somewhere. And Chris is the one who always comes up with a plan B or C to counter the possible chaos. Also, a shout out to Ashley Tarrant, who has created our beautiful poster. We will be sending an email out to all of you just after this presentation with a very short survey asking your reaction to what you have heard today. So please take the time to answer the questions because your responses are really helpful for us to inform our future program design. So from all of us to all of you, thank you. Wado, ayehe, and gracias.
Thank you so much. Thank you.